Hello guys, welcome back to our channel EC TechNest. Today we are in the day 14 of the Verilog and Digital Architecture series. Today we'll be discussing about an important concept in sequential circuits, that is latches. Different type of latches that you can see is SR latch, gated SR, D latch and JK latch. Here it is the simplest form and has an invalid state 1 comma 1. That means in 1 comma 1 when your inputs S and R are both 1 1, you will see a state where there is a indeterminate state. And for gated SR, you have S comma R enable. This is important because it provides better timing and improves the race around condition. D latch. D latch is with an enable, no invalid state. Output follows input whenever it is enable is high. JK latch, JK enable toggles when J equals 1, K equals 1, prone to race condition. We'll also talk about one more latch, that is T latch. It is an addition to the JK latch. SR latch. The SR latch is the most fundamental building block. It can be constructed using either NOR or NAND gates. That is, first one is set forces the output Q to 1. Reset forces the output Q to 0. Let us check how it works. Whenever your as inputs are 0 and 0, right? R is 0 and S is 0. The output will be dependent on the previous state. Whatever is there in the previous state, that will get latched. If your input S is 0 and R is 1, it forces the output Q to be 0 and Q bar to be 1. And if it is 1 0, you will get 1 0. In the other case, in the last case, we hit the 1 and 1 where it's an invalid state, because here you can see that you are not able to put a Q. If Q is 0, Q bar has to be 1, right? That is not happening here. So this will become an indeterminate or invalid state. So we come to the concept of gated SR latch. To prevent the output to be changing randomly, an enable or a clock signal is added. The latch only listens to the S and R inputs when the enable signal is active. To be understanding it exactly, let us see here. Whenever the enable signal is low, it means that the our output will hold on to the previous value. And when enable is 1 and the inputs are 0 and 0, still it will hold on to the previous value. But when enable is 1 and the condition is that S is 0 and R is 1, you will get 0 1. So your output will be 0 and your Q bar output will be 1. Here again, when enable is high, you will get 1 as the output and 0. Again, for gated SR latch also we have this invalid state. This is how you can write your behavioral SR latch code. You are writing the input, that is S, R and enable. Output registers Q and Q bar for this diagram. R, E and S are inputs, Q and Q bar are outputs. Then if enable equals begin, if S is 1 dash B1, that if S input is 1 and R input is 0, our Q will be 1 and Q bar will be 1 dash B0. Else if S is equal to 0 and R equal to 1, your Q will be 0 and Q bar equals 1. And another condition is, if S is equal to 1 and R is equal to 1, this is an invalid state. That means it will give an X. And here we are ending our code with an AND module. Now we'll go to D latch. D latch is nothing but here it is used to eliminate the forbidden state. So let us see how it eliminates it. It ensures that the inputs to S and R terminals are always complements of each other. So if what they're trying to do is, if you're giving one thing as an input, the other input whatever you're giving, it will make sure that it is a complement. So if your D is 1, it will make sure that here when the D is going, it is 0. So this avoids the invalid state whenever your inputs are both 1 and 1. So let us see, when enable is 0, it will still latch. So only when the enable is high and your D input is 0, you will get output Q as 0 and Q bar as 1. And when both are 1, you will get Q as 1 and output Q bar as 0. So our invalid state problem is solved using a D-latch. Module D-latch inputs are D and enable. Your output two registers, that is Q and Q bar, always at D and N. That means whenever at these two cases, and if enable is high, begin. Q will be equal to D. That means whatever is there in this Q, right, that will be in D. It means whatever is in your previous state Q, that will come to as D. And Q bar will be the negation or not gate of D. And you will end your module, end the always block and end module. Next we have an important concept, JK latch. A JK latch is essentially modified SR latch that resolves the invalid state through feedback. Okay. What happened in D latch? We just tried to solve it using a NOT gate. But here you have again two statements. Jump acts like set, K for kill acts like reset. If both J and K are high while the latch is enabled, output toggles. Let us see how it works. So you have your normal SR, whatever you had the same gate logic, but what happens is this output is given as feedback. Whatever input output we got from Q bar, it is given back as input to the what is this NAND gate. Again, whatever output we got at Q is given back as input to the NAND gate. Let us see how it works. When J and K are both 0 and 0, there will be no change. When it is 0 and 1, you will have a reset state. 1, 0, you will have a set state. And 1, 1, it will toggle. You will understand it better through a code. Here, same. You should write about all the inputs and the outputs. Then always at JK enable. If enable is high, the case is I'm checking the values of J and K. So if J is 0 and K is 0, whatever was in your previous state will be the same. It will hold the state. If it is 0, 1, it will reset. That is, it will again come back to 0. If it is 1, 0, it will set the state. If it is 1, 1, it will toggle. Here again race around condition will happen. Let us see how we can solve that. What is race condition? It is very important to understand what is race condition. This mostly occurs in a JK latch when J is 1, K is 1 and the enable signal is high. In this state, the output Q is supposed to toggle. If Q was 0, it becomes 1. If it was 1, it will become 0. What they are trying to tell is, here, since we are giving the feedback, right, this loop will continuously repeat. If Q is 1, it will become 1, right? And if it is 1, it will become 0. The problem is, because the latch is level sensitive, as long as the enable signal is 1, the output will keep toggling. The race, the output Q is fed back to the input gates. The change in Q travels through the feedback loop. That is what I told. The feedback loop is again triggering a toggle condition. It solved the invalid condition, whatever was there in SR latch, but it got another problem, that is toggling. This continues in a loop. What happens is the output becomes unstable oscillation, shaking between high and low rather than a clean state change. So to solve that, again we got a T latch. So what we do in T latch, instead of giving two inputs that are J and K, we'll give it a single input, as we short J and K together and give a T input. Why T latch still has that race condition? Let us see. In your JK latch code, the race condition occurs when J is 1 and K is 1 and enable is also high. Since a T latch is made by tying J and K together, it means we are shorting it. When T is 1 and enable is 1, the circuit is told to toggle. The output Q flips from 0 to 1. Here, when the input is given, the output Q will flip from 0 to 1. Because the enable is still high, the circuit sees the new Q, feeds it back and flips it again 1 to 0. Here it is telling, since they are giving feedback, right, it has become from 1 to 0, But since again a feedback is being given to the input, what will happen is it will again change to 0 to 1. So what I mean to say is T latch also has a race condition, but due to this mechanism, since we have shorted both J and K, what happens is this keeps continuing 0 to 1, 1 to 0. So it is like running in a loop. This continues as a rapid uncontrolled oscillation until the enabled signal drops to 0. See, you can see T latch, it is just connected. But what we are doing, main thing you have to see is the J is instantiated to T. It means both input of J and K are given to the same input T. So it means we are shorting it. If you have any doubts, feel free to put it in the down in the comment section. Thank you.